Now to get to why you are actually here this morning. Brian Kernighan. Brian Kernighan received his PhD from Princeton in 1969 and was in the Computing Science Research Center at Bell Labs until 2000. He is now a professor of the Computer Science Department at Princeton, where he writes short programs and longer books. The latter are better than the former and certainly need less maintenance. Brian will be speaking to you about the early days of Unix at Bell Labs. I'd like to hand over to Brian now.
Okay, thank you very much, Miles. I'm going to assume that I'm properly on the air. And also thank you to the incredible collection of tech support staff who are behind the scenes here, who in principle are making it all work. So it's genuinely a real pleasure to be with you either today in the morning, which it is in most of Australia, or in the late afternoon, as it is where I am in New Jersey. It would be wonderful to be back in Australia, but that's not going to happen in the near future. So in fact, this is where I am. I'm in Princeton, New Jersey, which is roughly 75 kilometers southwest of New York City. So that places it. I've only been in Australia once. It's something I would love to remedy in the future, but it's a long way to Sydney, which is the place that I spent most of my time visiting when I was in Australia in 1984 or something like that. Long time ago, something that obviously should be remedied. So one of the reasons that I can talk to you so easily from my home in New Jersey in the United States today is that we have the internet to connect us. And of course, most of the software that runs on the internet, that runs our computers, that supports the kind of remote conferencing systems like the one we're using here, is based on Unix and Linux, the operating systems that we all know. So the Unix operating system was actually created just over 50 years ago at Bell Labs in New Jersey, not too far from where I am. So here's another version of that map, New York to Princeton there. And Bell Labs is essentially exactly where the X is, somewhat west of New York, somewhat north of Princeton. So what I'm going to do today is to talk mostly about the early history of Unix, how it came about, how it grew over that early years, and maybe talk a bit about the evolution of Unix, perhaps teaches us something about how software development can be done effectively, and perhaps how to manage people and processes to make them as productive as possible. So, what is Bell Labs? What was it? Let me give you a little bit of history. So in 1885, boy, you lose track of time. In 1885, AT&T, the American Telephone and Telegraph Company, was founded. And essentially over the next 30-ish years, it came to provide telephone service for the entire United States. And it was a big, complicated operation to do that sort of thing. And the company realized quite early that they needed technical expertise to be able to provide this basically highly technical service. And so they created a part of the company, which they called Bell Telephone Laboratories, to do research, to figure out how to do things better so that telephone service could be improved. And that was originally in New York City, very close to the, right on the Hudson River on the west side of New York, in 1925. And then it was moved to suburban New Jersey, X marks the spot, in about 1960. And so this is what Bell Labs looked like from the air at the Murray Hill, New Jersey location in 1961. And you can see it's a pretty big place. You get a sense of the scale from the size of the cars in the parking lot scattered around it. And the operation at Murray Hill basically did research in primarily physical sciences, things like physics and chemistry and materials. And there were about 3,000 people working in research in this operation, at least 1,000 of whom had PhDs. So you can think of it as a very large specialized university, but without students. And an awful lot of important inventions came out of that. The most obvious one is the transistor, perhaps, but the laser, fiber optics, and a wide variety of other things. And over the years, depending on how you count them, 8, 10, 12 Nobel Prize winners as well did work at Bell Labs. So that was just the research part. Then there were roughly, call it 25,000 people at peak in a part of the company that was also called Bell Labs, which focused on development. That is, taking things from research and trying to convert them into things that would actually be useful in the providing telephone service. And then Bell Labs was a small part of AT&T. At its peak, AT&T had well over, 1 million employees, and so it was a very, very large operation. As I said, most of the work at Bell Labs was in the hard sciences, physics and chemistry and things like that. But there was also quite a bit of work in mathematical things and communication theory. And here are two of perhaps the most important people who worked in that area. Claude Shannon, the creator of information theory, who I never met, and Dick Hamming, the creator of, among other things, error correcting codes, who I knew extremely well for many years. It's actually kind of intriguing that Claude Shannon and Dick Hamming actually shared an office once. And if you can imagine an amazing experience, what that must have been around there. So anyway, I actually went to Bell Labs in 1967, I guess it was. There were about 25 people there doing research in what was called the Computing Science Research Center. It had been newly created by spinning off some people from the Mathematics Research Center, which is where Shannon had been, although he had since moved on to MIT. And they worked on things like programming languages, tools, operating systems, things like that. And they were mostly located on the top floor of what was called Building 2. And so Building 2, you can see two little red dots there, and you can see the arrows pointing at parts of that. So they were on the 5th floor of that building. And I arrived there in the summer of 1967 as an intern, one of these lowly people. The red dots are my offices. The first one was in 1967, and it was next door to Dick Hamming. And so this is kind of an interesting way to start a career, to put it mildly. I spent the summer of 67 there. I came back for another summer in 68, and then I came permanently in 1969. And my office in that entire period of time was at the other red dot further along the corridor. So very interesting kind of operation and an amazing place to be. The people who were in the Computing Science Research Center at that time were, as I said, working on various kinds of software like programming languages and especially operating systems. And so in 1961, MIT created a system called CTSS, the Compatible Time Sharing System. And it was led by Fernando Corby, who was an amazing, nice guy and a very, very forward-thinking kind of computer person. So CTSS, created in 1961, was a time-sharing system. That is a system where there was a single computer and people accessed it from basically remote devices, sort of like cloud computing before there was such an idea. It was such a success that people at MIT said we could do this better, and so they designed a system which was called Multics, the Multiplexed Information and Computing Service. And the idea really was an information utility, something like cloud computing today. And it was going to be new and improved and better in every single possible respect. So this was a big job. And so MIT enlisted the services of two other organizations. One was General Electric, which at the time made computers, big computers. And the other was Bell Labs, which at the time had a great deal of expertise in programming languages and operating systems. So what you have there is three different institutions, geographically separated by very wide distance, roughly the distance from Sydney to Perth, let's say, in the case of General Electric, and very different organizations, a university, a research lab, and a profit-making company. And you don't have to be much of a student of institutions to realize that this was kind of a recipe for things not working super well. Multics was late. It didn't at least in the early days, worked well. And so in 1969, handwriting on the wall, Bell Labs withdrew from the project. And this left people like the folks on the bottom row there with nothing to do. They had gotten a taste for really nice computing environment. They had understood what kinds of things could be done with computing in a variety of ways, but they didn't have any resources anymore. And so they spent quite a bit of time in 1969 trying to convince management to buy another computer, a big computer, so that they could work on providing information utility. Management, once bitten, twice shy, said, and they stalled. They continued to stall. So in the meantime, Ken, Thompson, Dennis Ritchie, Doug McElroy, and others spent their time thinking about what would be an interesting way to build a system that people would like to use. And Ken Thompson, not theorizing, but just going and doing things, found what has been traditionally called a little used PDP-7. So this was a machine that was first released by DEC in 1965. It was by 1969 obsolete, and that's probably the reason why it was little used. But Ken did some experiments with it. Basically, he was trying to see whether you could make file systems run better, whether some of the designs for file systems that they had been doing on blackboards would actually make sense. And so what he did, and I asked him about this because it was sort of folklore and I wanted to get it straight from the horse's mouth. So sometime after he and I had both retired from the labs, I sent him mail saying, gee, Ken, I heard this story. What do you have to say? And this is what he said, that Unix was a file system implementation to test throughput, okay? It was hard to get data loaded up. He could read and write, but, it was impossible. And so, but his wife, Bonnie, was going off to visit family in San Diego, California, across the country, and was going to be away for 3 weeks. And so Ken said to himself, all it needs is a couple of things. Fundamentally, an exec call, trivial, a shell, an editor, an assembler, okay? A week each. And that was the original version of Unix. Now, this is a definition of software productivity, which I suspect most people here have never encountered before. I certainly haven't. And the whole thing was done on a machine which is infinitesimal. It had 8K 16-bit or 18-bit words. Okay, so half of that was the kernel and the other half was users being swapped in and out. Pretty amazing. So the PDP-7 was what we'd call, I guess, proto-Unix, useful, but very, very limited. And so Ken and Dennis spent some of their time continuing this lobbying for, can we get a bigger computer? Management continued to waffle and stall, but finally, the group managed to cobble together enough money to get the brand new, at that time, PDP-11. DEC released this machine in early, I think, 1971, and Bell Labs got one of the very earliest of those. It cost $50,000 at the time, which is still a chunk of money, but not a huge amount. And the value proposition, to use a phrase, was that the people who were interested in this would write basically a document preparation system that would enable the Bell Labs patent department to produce patent applications in the official required form far more easily than could be done with commercial word processing systems. And so that is a very famous picture, PR picture, of course, of Ken and Dennis in front of the PDP-1120. Ken is seated, Dennis is standing. And you can see a lot of things about old computing, including the fact that those were Model 33 teletypes, were rolls of paper and things like that. But that was enough to build what would be called the first version of Unix, the first edition, which appeared in 1971. And at that point, the system was in use by real people. It was completely self-supporting. It was recognizably Unix. If you logged into it today, you would say, oh yeah, I recognize that. It supported multiple independent users, so it was a time-sharing system, and it was really well documented. It had the famous man page style like this. So this is the man page for the cat command. Notice the date, November 3rd, 1971. And that cat command still exists to this day. That is how you do things like copy a file, print a file, and things like that. It introduced even the famous bugs section, although cat appears to have no bugs at this point. Maybe that's no longer true. And so that's the beginning, if you'd like, of Unix. Now, there was an early market forecast, I guess. The second edition of the Unix Programmer's Manual, which appeared sort of 7 or 8 months later, said that the number of Unix installations has grown to 10, with more expected. Okay, and we wouldn't be here today if things hadn't gone slightly better than that. What followed then was a sequence of very rapid evolution with a new edition of the Unix system roughly every 6 to 8 months for some years. And most of what I'm going to say in those dates is based on, in fact, the historical record, which is maintained by this wonderful operation called the Unix Heritage Society, which is, of course, based in Australia, worked by Warren Toomey and others. And the Unix Heritage Society has been collecting historical documents, code, you can download versions of the code from many, many early Unix systems. And basically, it's just a historical record, and it's a very active group. I literally got mail from a friend asking me to weigh in on some discussion of document preparation systems that's going on. I got mail from him about the discussion going on in the Unix Heritage Society about 3 hours ago. I haven't gotten around to answering him yet, but so it's a very, very active and interesting group. And if you haven't done it, go for it, and appreciate the work done in Australia on this. Okay, so among the other things that happened with those early days of Unix, the first versions of Unix were, of course, written in assembly language, first on the PDP-7 and then on the PDP-11. But one of the lessons that had been learned in the Multics environment was that it was possible to write code in high-level languages, and that was obviously a lot easier. And so one of the big contributions there was, of course, the development of the C programming language by Dennis Ritchie in roughly the period 1972 or 1973. The Multics system had been explored a language, PL1, but that turned out to be too big and too complicated. And so a lot of Multics code was written in a language called BCPL, which was done by Martin Richards at the University of Cambridge. Ken Thompson took BCPL, which was already a fairly minimal language, and stripped it down even further into a language which he called B. And Dennis then derived C from that. Basically, BCPL and B were typeless languages. C had different data types to reflect the fact that the PDP-11 had different data types supported by hardware. And so C was a language then for system programming, based on that experience with Multics. And as I suspect everybody here knows, C is sufficiently expressive and efficient to do anything really well. And it's, in some sense, hit a sweet spot in the design of programming languages that's been hard to follow or match ever since. And certainly locally, what it did was to lead to this incredible explosion of applications, most of which were system programming kinds of things, tools and things that helped programmers do better. Some of the obvious ones were YAC, the compiler that Steve Johnson created, that made it possible to create language translators, compilers very easily. Lex, a similar program for lexical analysis, which was done by Mike Lesk shortly afterward. And those, of course, then in turn led to all kinds of languages and tools, document preparation, and so on. So I think the most important of these might be the portable C compiler that Steve Johnson did, which led to the portability of the operating system itself, because the observation is that if the operating system is written in a high-level language, then in principle, you can move the operating system to another computer if that other computer also has a C compiler. So I'm going to come back to that in a couple of minutes. But there was something else that happened at about that same time. The Unix system was up through version 3. The third edition was written in assembly language. The fourth edition was in C. And of course, never looked back since then. Something else that came along a little even before that, which is in a way very characteristic of Unix, is the invention of pipes. So here is a paper, I don't know, I guess you'd call it a white paper or something, that Doug McElroy wrote in 1964. It's kind of hard to read, perhaps, so I'll put up a clearer version of it here. But the gist of it is, and this is something that Doug had been flogging for a long time, the idea that what you could do is to have some way of connecting programs together. And his metaphor was like, couple them like garden hose. You just screw in another segment when there's something that you want to do some further processing on this. And so this was Doug's idea. And it didn't actually make it into working code until some while later, but it fundamentally arrived in time for the third edition of Unix system, which appeared in early 1973. So this is a late 1972 invention, the idea of pipes and then pipelines and filters. And of course, everybody here knows all about that stuff. And so it's probably hard to imagine just what an incredible revolution it was in the way you thought about programming at the time. It was one of those things where I still remember this idea of, gee, you could connect the output of one program to the input of another. It's really easy, and you can do really neat things without any work. So who, remember, it's a time-sharing system, so lots and lots of users potentially on the same machine. So who gives you a list of the users, one line per user. Grep, our pattern searching program. Let's look for all of the users named Joe. And how many of those are there? We'll run it into word count, and so who produces a bunch of lines, grep selects some of them, a word count tells you how many lines there are, and that's the number of times that Joe is logged in. So when the pipe mechanism came on, and it was really, really trivial, Ken says that it took him less than an hour to put it into the operating system because all the other mechanisms were already there. And that it might have taken others longer than that. But people started to invent interesting ideas. And they spent a lot of time very quickly modifying programs so that they would actually work in pipelines. So if you think about the sort command. The sort command takes input, sorts it, and then produces output. But it cannot produce any output until it has seen all of the input. So putting it in a pipeline is in some sense deceptive, right? Because that's a dead stop in the pipeline until you've seen all the input. But as a packaging matter, as an engineering and making it easy to use matter, you package it as a pipeline, as a program that is just another filter. It's a filter that sorts. And so that kind of insight led to all kinds of intriguing ideas. The pipeline for detecting spelling mistakes is due to Steve Johnson. You take a bunch of files, you canonicalize them in some way, like convert uppercase to lowercase. You sort them. There's that dead stop in the pipeline, but it doesn't matter. And then you pick out the words, the unique words. So if the word THE appears a bunch of times, you only care about it once. And then you compare it to a dictionary and print the words that are in the document, but not in the dictionary. And there is a first draft of a program for detecting spelling mistakes in documents. And how long did it take to produce that? You could practically write that without even putting it on paper first. And on a larger scale, and this is where stuff that I was more interested in at the time, was the idea that you could modularize programs by having a sequence of programs, each of which did a part of a job, but make them work together. And so the part that I was most interested in was the document preparation tools, TROF, which basically did formatting. Think of it as an early version of a program like TeX or LaTeX. But then a special program for mathematics, which Lorinda Cherry and I did, a special program for tables, which Mike Lesk did, and then some drawing pictures, and so on. So all of that idea of taking something that would be an enormous ball of wax if it were a single program, but instead it's a sequence of programs that each does its own thing, and they collaborate to get a job done. And so that idea of basically tools, of thinking about what you're doing, is not so much writing programs, but is building tools that make it possible to do things very easily, is I think one of the pervasive ideas in Unix, one of the things that's most distinctive. And certainly there's a bunch of these small tools like grep and diff and so on. There's the shell itself, which is programmable. So it's a programming language whose operators are programs. It makes it easy to combine programs to do things. And then we have tools for making further tools, in particular language-based tools. And then we have more tools that are programmable. And then, of course, that leads to languages. And so this metaphor of the building blocks, I think, is in some sense a very, very nice example of how Unix works. And this is a PR photograph from probably the early 80s or something like that, late 70s. And hiding in the background, it's hard to see, although I know of it, is a TROF document. And I know because I provided the TROF document that's in the background. I have no idea what it was about. So anyway, let me talk for a minute about grep, because it's actually kind of an interesting story. And grep is, in a way, the quintessential example of a small tool that started with Unix and in some sense was the place where we started to think that what we're doing is building tools. It was created by Ken Thompson literally overnight by surgery on the ED text editor. He basically just threw away everything except the pattern matching part of it. And the result was a tool which is absolutely fundamental. I suspect that anybody who has used their Unix or Linux box today has probably used grep for something. Certainly I have used it probably a dozen times already today. There's a wonderful story that goes with it. I got a call, and it must have been in 1972 or 73. And a guy called me, and I was at Bell Labs, and he said, I just got a new HP 35 pocket calculator. Now, this was the first real serious pocket calculator, and it came out in 72. So let's call this 72 or 73. And he said, I understand that you guys have a dictionary on your computer. And I said, yes. And he says, there's some way you could use that dictionary to tell me what words I could make on my calculator if I hold it upside down. Well, I was in a research operation. You're sometimes disconnected from reality. So it was nice to have a guy call with a real practical problem. And so I said, sure. What letters do you think you can make when you hold it upside down? And he said, I think I could make BEHILOS. Now, this is pretty crappy looking here, but you get the idea. And so I said, okay. And so I typed this command into my terminal. grep, we've talked about the pattern matching program. UserDict Web 2 is the word list from Webster's Second International Dictionary. Just the words, one word per line, 235,000 words. So it's a big word list. And the thing in the middle is a pattern. It's a regular expression. It's one of those things that's absolutely characteristic of Unix. And it's a pattern that says, I want to see lines that contain only arbitrary combinations of any number of any of those letters and nothing else. So I typed this command and I pushed return, and out came an amazing list of words. This is probably hard to see unless your projector is very good, but there are 263 words there. I am a pretty well-educated native speaker of English, and there's a boatload of words there I've never heard of. I have no idea what they mean. But anyway, I printed the list and I sent it off to this guy, and I think he was probably happy. I never heard from him again. But he left me with this wonderful story of the importance of tools, the idea that if you have the right tool for the job, you can do something which would otherwise be either not possible to do, or certainly not worth doing. So, great example. So I think all of this stuff fundamentally came together in the 6th edition of Unix. The 6th edition was and you notice May 75, so we're roughly 3 and a bit years from the 1st edition. This was the first widely used version, the first version that was used outside of Bell Labs in any new real sense. And it had a bunch of things that are characteristic of Unix to this day. The hierarchical file system, where the files are just bytes, the devices are files in the file system, and the other things that I've mentioned, like the shell and the pipes and so on. And as I said earlier, the system was actually written in C for the 4th edition. So it was about 9,000 lines. There was a certain amount of assembly language, but the vast majority of it was C code. Okay, and because of that, it was comprehensible by people. you wouldn't want to have to deal with the equivalent of 9,000 lines of C in assembly language. It would be just a nuisance. And the accessibility of the code in C, a language which was understandable, led to some really interesting things. And here's one of the best of all of them. This is the commentary that John Lyons produced on the 6th edition code. So what John did was to take that code, 9,000 lines of C and a bit of assembly language, and basically produced two side-by-side books, one of which had the code, and the other which was an explanation of what every single piece of that code did. And it's a really, really marvelous book. And I don't know whether it's still widely available. I have a numbered copy because originally they were very, very closely held. This surreptitious-looking pair Xeroxing. It suggests that it was not meant to be distributed widely. But it's a really, really excellent description. Ken's observation about best exposition of the workings of a real operating system, I think, is absolutely true without even the need for quotes around real. John, of course, was at the University of New South Wales in Sydney, but he spent several sabbaticals at Bell Labs in New Jersey, and his first one, which was 1978 and 1979, he spent it in the office across the hall from me. So I knew him well from that. The book is, of course, one of his main legacies, an absolutely wonderful book. Another great legacy is an amazing collection of students who went through his courses at University of New South Wales and then went on to a variety of other things. Several of them wound up at Bell Labs, where they become good friends as well. And of course, John was my host for my trip to Australia in 1984. It was a wonderful time. The conference was held in the Sydney Opera House. I spoke at the very beginning of the conference and then spent the rest of the conference looking out the window at the harbor. I have no idea what anyone else said, but I had a wonderful time. One of the high points of the visit was dinner at John and Marianne's home in Sydney. And I remember that fondly. The part I don't remember quite so fondly is getting back into my car to drive back to my hotel and discovering an absolutely enormous spider in the car. So I'm sure Australians are all chuckling over this. But for the tourists, it was one big spider. So anyway, there is John Lyons with some of his students and a very characteristic picture of him. So I mentioned the fact that the operating system was written in C and thus was potentially portable to more than one kind of computer architecture. The first port of Unix to another computer was actually done by Richard Miller at University of Wollongong in April of 1977. He ported it to an Interdata 732. About 6 months later, Steve Johnson and Dennis Ritchie ported it to an Interdata 832, which is similar but not quite the same. And then there were ports to the then new VAX computers at Bell Labs and then at Berkeley. In a sense, that shift from the PDP-11s to the VAX computers was also a shift in the center of gravity, and a lot of it went on in several different directions. There's activity at Bell Labs and AT&T, who are trying to make a commercial version of Unix, and a lot of activity at Berkeley, where in particular they were interested in networking. But this was all enabled by the portable nature, writing in a high-level language and thinking about portability. And that portability of language and operating system and all of the tools, all written in C, enabled the workstation market, which was companies like Sun Microsystems and MIPS, which became SGI, and Apollo and Sequent, and just a bunch of others. And then a few years later, 1982 or so, the IBM PC. And this is something that I think is not really well known, but for Microsoft had their own version of Unix. It was called Xenix. And for a period in the 80s, Microsoft was the biggest distributor of Unix operating systems. And I keep thinking, what would the world have been like if Microsoft, instead of going off and DOS, had taken off with Unix? Who knows what would have happened, but it certainly would have been interesting. Okay, so anyway, this is kind of, at this point, let's call it the mid-'80s, what I would call the golden age. Okay, so Unix is everywhere. It runs on all the computers that anybody has made. C and derivatives like C++ are on everything as well and used for all kinds of things, even on non-Unix systems. Lots and lots and lots of languages and tools that are used by all kinds of people, and recognition in a variety of ways, both public, gee, what is this Unix thing? People had started to hear about it, and recognition, in serious recognition for the people who had done the work. For example, a Turing Award for Ken Thompson and Dennis Ritchie in 1983, and somewhat later, an interesting further one, National Medal of Technology with Ken, Dennis. This, I think, is the only time I've ever seen Ken wearing a tie, with Bill Clinton. So interesting picture. So that's kind of recognition. There was also the appearance of Unix in what we would call popular culture. I'm wondering, I don't know how old, because I can't see any of you. I have no sense of the age of the audience or your entertainment taste or anything, but I suspect there's at least a few people who remember Jurassic Park, which appeared in 1990. Okay, Jurassic Park was a pretty decent picture, I think. I certainly enjoyed it. But the thing that made it special for an awful lot of geeky people like me was this observation of, it's hard to, it really is fun to see that. Lex, the young woman who is 12 notionally in the movie, understands that she knows how to use a Unix system and turn on the safety systems that capture or lock the velociraptors back in their cages or something like that. And so this is the high point of the movie for anybody who is a geek. The other thing is a little hard to see, but this is, of course, being done on a Silicon Graphics workstation, a standard, nice Unix system. And in fact, a lot of the graphics for the movie were done on SGI systems. Okay, so this is the peak in some sense. But I think that there were sort of a lot of external forces that started to take a toll in the late 80s and early 90s. AT&T and Berkeley got into a legal contest with each accusing the other of doing bad things, in particular AT&T saying that Berkeley was stealing intellectual property. And that lawsuit was completely pointless. And also what it did was to kind of fragment the world into people who were following the AT&T side of it and people who were following the Berkeley side of it. And you got divergent versions. And it took a long time for any kind of standardization to bring that back. There were contributions from all over the place. Some of them were not as good as others, I guess. Hardware got cheaper, which is good, but it meant there were fewer constraints, which meant, I think, that people didn't think as hard about what they were doing sometimes. And of course, a big effect was the growth of the PC and Microsoft, and the shift of talented people and good ideas to a different world, a world which is much less focused on command line stuff and much more focused on interaction, user interfaces, graphical stuff, and applications over a wide range of things that are not system programming kind of things. So that was kind of a divergence or whatever, but then something interesting happened. And it happened, in fact, you can date it almost exactly, August 1991. Linus Torvalds announced the availability of an experimental system that he was building. It was sort of aimed at people who are using Minix, which is Andy Tannenbaum's educational version of Unix. And he's doing it for fun. It's not a big deal, but he's done a lot of stuff. And if anybody's interested, contact me, I'll do it. And he says down there at the bottom, it's not portable, and it'll probably never support anything other than certain kind of hard disks and so on. So, yeah. And so this is interesting because Linus is just as wrong in his market forecast as the original Unix folks were in theirs. So at that point, the rest is history. Okay, so I cobbled this together from something that purports, now it's a Unix Fan Club kind of thing, but it purports to report accurately, and it does report accurately, that all of the top 500 supercomputers run on Linux, and most of the big websites and servers and so on are all really using Unix, and of course, or Linux rather, and of course we're all doing the same thing for conferences like this one. So there's a technical legacy that goes with Unix. I think the first three arguably come pretty directly from Multics. It's not like Unix sprang out of nothing. Multics had an enormous number of good ideas and showed the feasibility of some of those quite well. And those were simply adapted and streamlined in some ways and used in Unix as well. I think pipes are unique to Unix, and then that the pervasive use of tools and regular expressions and so on, all these things are at this point very characteristic of Unix. And the other thing that went with it, which I hinted at when we were talking about tools a bit, is a philosophy of how to create software, how to try and produce software by using a relatively small number of programs that do one thing well, and then you try to make them work together with each other. Okay. So I think you could say that the essence of Unix is at this point about 50 years old. And this slightly snarky comment from Doug about Unix being an improvement on its successors. But I think arguably there's a grain of truth in that. An awful lot of Unix was actually right there in place in the 1975 6th edition, the one that John Lyons documented so well. And are there great new insights or ideas since? I'm not sure. Certainly, there have been changes. The most obvious things since the 7th edition are things like networking, which, of course, that's what we're using right now. Multiprocessors increasingly have more and more and more cores that are working on things in parallel, and that's a very different environment than the original Unix machines. Graphical user interfaces, more and more, but not as stable as they might be. And of course, the realization that lots and lots and lots of parts of the world do not use the United States version of characters, that ASCII is not sufficient. So lots of things. And then finally, scale, that most Unix systems are dealing with very, very, very large environments at this point, far beyond anything that was thought of in the early days. So how did this all come about? I think arguably it wasn't, not arguably, it was not planned. It was an accidental combination of a whole bunch of factors. First, and this is really the critical thing, two exceptionally creative people, Ken Thompson and Dennis Ritchie, with exceptionally good taste. I mean, their taste for minimal mechanisms and finding the generalities, the cleanliness of what they're doing is very, very perhaps unique, and certainly a good supporting cast in a variety of ways. Management at Bell Labs was technically talented and typically very, very benign. It was not, here's what you have to do, and every quarter tell us what you've done. It was more like, oh, gee, you're doing that? That sounds really interesting. Why don't you keep doing it as long as it looks good? And Doug McElroy, perhaps an unsung hero of the Unix world, was the manager in charge of an awful lot of this stuff, and he led by example and was just an amazing contributor to the whole thing. Now, of course, a lot of this depended on the fact that hardware was comparatively cheap, that the first Unix system was able to run on a machine that cost $50,000 instead of $500,000, and then smaller workstations came down that were even cheaper than that, and then PCs. So the technology improvements fueled an awful lot of this. And then finally, the Bell Labs environment was particularly congenial for this kind of thing, and that's something which I don't see as much of today, perhaps. But funding was stable because it was basically run as a, Bell Labs was run as a tax on the telephone service in the United States. And so stable funding and a stable organization and a very long-term view of what was useful. And the environment itself was incredibly cooperative, collegial, and just a lot of fun. So could we do this again sometime? I don't know. I would say, well, first, obviously, they're always good people. No particular part of the world or organization or anything else has a monopoly on really good people. Dilbert cartoons notwithstanding, there are good managers, and hardware continues to be dirt cheap, and lots of great software. The open source software that we see so much of, like Linux, is free. And so all of those things are very, very positive. On the flip side, there are not as many of these unfettered environments where people are simply set loose and told to go and do something that they want to do that might be interesting or useful. It's hard to do that in industry because things tend to be short term, and it's hard to do that in universities because money. But in principle, it could happen again for something. And if you think about the number of things that we use in our field every day that began with one or two people and a good idea. Linux is the obvious thing. That's one guy, okay? And certainly there's a cast of many, many thousands at this point, but that was one guy with a good idea. Languages that we use, C++, Java, Perl, Python, PHP, Ruby, JavaScript, Go, just the list goes on. And all of those are the work of just one or two people to get off the ground. And then, of course, the big companies that we deal with as well, like Microsoft and Apple and Google and Amazon and Facebook and on and on and on. They're also one or two or three good people with a good idea. So stuff can happen. So I wanted to close with an observation from Dennis Ritchie. So Dennis died about 10 years ago, last October. But what he said here was fundamentally that Unix was meant to provide a community. It was sort of a warm and welcoming place to develop software. So it brought people together. And certainly in the early days, people enjoyed their work. They enjoyed the people they worked with. And so it was a very positive cycle of productive environment for all of the people. And so I think what we want to do today is that same kind of thing where we have that sense of community that we're working together to try and do things that will in some way make the world better. And this conference is a great idea with lots and lots of people coming together virtually to learn from each other and hopefully to continue to improve what's going on. So it's been great fun for me to be a part of this, and I hope it has been fun for you too, and I hope the rest of the conference goes extremely well for all of you. So with that, thank you very much.
Thanks, Brian. That was really interesting. We should now have, hopefully, we have our live Illustrator feed we could probably pop in here, and you should be able to see it on your second screen, hopefully. There it is. So that's, you can have a look at that. I'll just run out. We've got a few more things to finish the session with. Feel free to, what are we doing? Oh, sorry, we're at the end of the beginning. This is our first break. Feel free to use the chat rooms or get away for a refresher. We'll return at 10:40 a.m. here for the start of our 4 Fab mini-confs. And don't forget to be back here at 5:45 p.m. this afternoon for the Locknote presentation from Kathy Reed. Thank you again very much, Brian. That was really fascinating. I like your definition of what a practical problem is in a research environment. When most people, they hear that word, they think useful, but, reading words on a calculator, not so much. Anyway, thanks very much, and we'll go to our break now.